In this section, we're going to talk about parallelograms, trapezoids, and a little bit about parallel projections. And we're going to start off with the definition. If we take a convex quadrilateral ABC, it says it is a blank if the opposite sides are blank. In other words, for the opposite sides being blank, opposite sides would be AB and CD. AB and CD. Those are parallel, and BC is parallel to AD. So what we have is a convex quadrilateral ABCD. It's called a parallelogram. If opposite sides are parallel. You have two sets of opposite sides, and they both need to be parallel as described right here. So here's a picture of that parallelogram ABCD. AB is parallel to CD. BC is parallel to AD. Now a parallel that has two adjacent sides congruent, that means they have the same length. Line segments are congruent when they have the same length. It's called a rhombus. RHOMBUS. So let's draw a picture of one. Be something like that, where all, well, what does this say? Two adjacent sides are congruent. So those two sides, for example, would be congruent. So those two have the same length. Well, what do you think must be true about the remaining two sides? Well, it turns out that they are going to be congruent as well. So by the definition, you only need to state that two adjacent sides are congruent. But if you have two adjacent sides congruent in a parallelogram, then it's guaranteed to have all four sides congruent. And in that case, we call it a rhombus. You could think of it as a square, then maybe tilted a little bit. And then lastly in this definition, a rhombus with two adjacent sides perpendicular. So we have to start with this rhombus, but we have to make two adjacent sides perpendicular. So it looks like this. Four sides, all with the same length. Everything is going to be perpendicular. What do we have? Well, that's a square. So a square is a rhombus, which is also a parallelogram. We're getting more specific. We started off with parallelogram, then a rhombus is a specific case of a parallelogram where all four sides have the same length, and then a square is a parallelogram with all four sides having the same length, but it has two adjacent sides which are right angles, which implies that all four of the angles will be right angles. All right, the next one, the next theorem. And we'll do a proof sketch of this theorem. So either diagonal, so just make one diagonal of a parallelogram, and it is going to divide that parallelogram into two congruent triangles. By the way, we know basically everything there is to know about triangles. So many of the proofs that we do in this section regarding parallelograms are going to be breaking it down into each parallelogram into two triangles. Well, let's prove that they would be congruent. Here's a picture of ABCD. It's a parallelogram, and I drew one of the diagonals. I could have drawn BD as the diagonal, and we will get the proof would be the same. I mean, it would be basically the same, only some of the angle numbers would be different. So we're going to prove it one way, this diagonal here. All right. How are we going to know that this triangle and this triangle are indeed congruent? Well, here's a sketch of the proof. The side line segment, it's not a side of the parallelogram, it's the diagonal AC, is congruent to itself. That's true about any geometric structure is congruent to itself. That's by the reflexive property of congruence. Ran out of room there. Reflexive property of congruence. That's what tells you that a line segment is congruent to itself. They have the same length. Okay, now how are we going to know that if this is a parallelogram, how do we know that angle 1 is congruent to angle 2? Here's angle 1. Here's angle 2. That angle and that angle. Well, this is a parallelogram, so we have two parallel sides. And what do we call the diagonal? That's the transversal. That's a line that's cutting through both of those parallel lines. So remember what that is? Property Z is the one that says that the alternate interior angles are congruent. So that's by property Z. And then how do we know that angles 3 and 4 are congruent? Same thing. That's the same property, property Z, because 3 and 4 are alternate interior angles. And that's enough information to tell us that triangle ABC is congruent to triangle CDA. Which law tells us that? Well, notice we have angle side angle being the same as angle side angle in the two triangles. So that's by ASA, angle side angle. So we just proved that the diagonal of a parallelogram divides that parallelogram into two congruent triangles. All right, there's a corollary, just some more mathematical facts. We won't prove them, although we may state how to prove them. And actually, the proofs will use the congruent triangles above. Remember, we have this as a parallelogram, and we've noted the angles that are congruent. What do we know about the opposite sides of a parallelogram? Opposite sides. So, for example, this side and this side. Well, they are congruent. Why is that? Well, it's because of corresponding parts of corresponding figures, of congruent figures, are congruent. This triangle is congruent to this triangle. So these two happen to be corresponding sides, so they are congruent. So we know the triangles are congruent by ASA. So if you have two congruent triangles, I just need to say for the reason, corresponding parts of congruent figures are congruent. Second one, opposite angles of a parallelogram are what? They're also congruent. Now, in the picture, what are we talking about when we see opposite angles of a parallelogram? We're talking about this angle and this angle. Or I could have picked the angle B and the angle D. But we've already got these ones kind of broken up. Why are the opposite angles? Why is this big angle and this big angle? Why are those two angles congruent? Well, we know that angle 1 and angle 2 are congruent. Angle 3 and angle 4 are congruent. That means that if you add up angle 1 and angle 3, you're going to get the same thing as if you add up angle 2 and angle 4. So that means these angles are congruent. Okay? All right, so let's see that again. I'm basically going to say that's true by same thing. Corresponding parts of congruent figures are congruent with a little bit of extra. The measure of 1 is the same as the measure of 2. Measure of 4 is the same as a measure of 3. So you add those two and add those two, you get the same value. And the last one. Adjacent angles of a parallelogram are what? Adjacent means two consecutive if you're going around like this, A, B, C, D, A, B, C, D. So for example, angle C and angle D, maybe I'll put 3 there on angle D, differentiate it. Angle C and angle D are what? Clearly not congruent because D looks like it's greater than 90, C looks like it's less than 90, so they can't be congruent, but they are supplementary. They add up to 180 degrees. Supplementary. And which property tells us that? Well, remember, we've got parallel lines cut by a transversal. It's property C. Property C is what would tell us that adjacent angles are supplementary. Let's see, we've got parallel. We've got transversal. Yeah, here's B, C, and AD are parallel, and then the transversal is CD. So if you take the angles on the same side of the transversal, they are supplementary by property C. And I'll remind you, supplementary means they add to 180 degrees.